Let's take a look at string theory, and we're going to consider a manifold that has 12 dimensions. So we need the two 10-dimensional uh, string theory, um, basically manifolds here. One that's a 3-1 spacetime with a positive complex volume, and one that's a 3-1 spacetime with a negative complex volume, so that these 6-dimensional complex volumes can act as dual spaces. So positive coordinates and then the negative coordinates, or complex conjugates. So we have this point right here at a singularity where we have a negative curvature space, which is essentially anti-de Sitter space. And then we have the positive curvature space, which is de Sitter space. And when we take the spacetime coordinates and we bring them all to zero, we do it a singularity, then the only paths left to move are going to be the dual complex spaces. So what does that mean? That means that oscillations at a singularity can only happen in these 12 dimensions, or two paths, 6 dimensions. So that leads us to degeneracy. Degeneracy is just the number of microstates available. And so we can think to ourselves, okay, so we had the 6 dimensions, and where did these two directions come from? Well, they're just the dual spaces here. And another way to think about this is two directions that you could take around a circle. Okay, the positive and negative oscillations. And so this gives us 6 times 2, which is 12. Now 12 is really important. 12 is a really important number. There's two numbers. Well, there's a really important sum that we need to look at to realize why 12 even matters. Because if we consider the Friedel sum, then we kind of want to consider 1 over pi times the degeneracy times a phase angle. Now, what's this phase angle? Phase angle is actually going to be the deficit angle that we get when we go around a black hole singularity. Because if we're taking a loop and kind of going around this, mentioned in another video, but if you try doing that, the circle is not really pi anymore. 2 pi. It's not 2 pi. So instead of being 2 pi, it transforms into pi instead. Right, so this is called a deficit angle, and this is what happens when you try to take a path around a black hole. You kind of just lose half of phasing. So you go down to a pi to get around the circle instead of 2 pi. Interesting. Well, that's good. So when we put that into our Friedel sum, we have 1 over pi times this pi, those kind of cancel out. We're left with 12 oscillations that we can take. And the 12 degeneracy, that corresponds to these 12 degeneracies. And that's important because, well, we want this to collapse down from, symmetry breaking into into the uh, into the standard model. So this is the standard model right here. The standard model is just SU3 times SU2 times U1. And that just means 8 gluons, 3 weak bosons, and 1 photon. So that just means that we have 12 different types of gauge bosons, or oscillation types, that we can have. And then we have 12 gravitational wave oscillations, which is these graviton oscillations. So we've matched the number of dimensions, the number of oscillations necessary to get the standard model from this 6x6 dual space combination. We just needed 12 dimensions that are sort of spinning off to the side, where we only care about a point in space-time, where this does not even matter. Meaning, we're essentially just saying just a point in space-time, and then what's happening on the side over here with the probabilities, because these are essentially probabilities. And this is spacetime. It's just the point. So probability to point. Well, that's interesting. We'll come back to that, I guess, a little bit later. Because, well, yeah, when we talk about these wave functions at a point, we do need to have wave functions because that's essentially what we're calculating at this point. We're calculating wave functions. So we have these closed strings that are oscillating around these two spaces. And these are you can kind of just see it right here, these little closed strings that are oscillating around these two curved spaces. So uh, when we say closed string, we're just saying the closed string and it's oscillating around two curved spaces. Okay, so where are we? We're kind of over here, and we're saying that we found the 12 gauge bosons based off of the gravitational wave oscillations was the graviton oscillations, based off of the 12 dimensions if we just pair two dual spaces. Um, all right. And so now we want to think about if these are closed strings, then they would have Hermitian Laplacians. So we could take a little spectral trace, and we could say, okay, let's take the Laplacian here on the positive curvature space, Laplacian on the negative curvature space, they're both six-dimensional, and then we kind of look at both of them, and we see that the eigenvalues should be equal to each other. Uh, so symmetric eigenvalues. That's interesting. Um, and as we take this trace, um, we realize that we kind of get this sum of all these different eigenvalues. Okay, we're summing up all these eigenvalues. So there's this massive sum of eigenvalues. And we're saying that we want to basically use a zeta function here and have this duality here of s. So 1 minus s is equal to s. So that way we can sort of flip these back and forth and have these interesting dualities happen. Why? Because wave functions and the complex wave functions are invariant, and we have to realize that there's two types of dualities. There's the S-duality and the T-duality. So the wave function duality kind of comes from this switching the s's, switching the eigenvalues back and forth, so that they should be symmetric eigenvalues. And when we have curvature duality, it's just T-duality, so we're just flipping the radiuses. So we're saying that inverse radii, positive, negative curvature. So that's the T-duality. And so now we ask ourselves, how on earth can we possibly have this possible duality? Because that's a very, very strict duality. We're saying that the complex curved space that's positive and the negative curved space, they have to have exactly the same solutions for these curves, for these closed strings that are wrapped around them. Again, it looks just like that. Um, well, there's more restrictions we have to impose. But this restriction is very interesting because this restriction basically says that in order for us to flip around this 1 minus s line, we have to have the ability to take 1 minus s, and whatever s we put in there equals s. How on earth is that possible? Because it's a very strange restriction. Well, if the real part of s was a half, like this, then we'd be able to take some IT over here and sort of start to flip them around and put them in here. And it turns out that that would actually give us uh, the same S back. So this kind of forces this, it kind of forces the Riemann hypothesis, right? That solutions on the critical strip, uh, they basically say that any solutions that are not on the critical strip are non-physical in this 6 by 6 12-dimensional solution space. Um, so yes, the eigenvalue solution are basically solutions of closed strings that are propagating in 12 dimensions, wrapped around these 6 by 6 complex little spaces. And any solution that's not on the critical strip are non-physical in this uh, in this universe. Okay, so it's kind of interesting. So now let's take a look at quantum operators because we realize that we need to have an inner product of these two wave functions, and well, they need to be normalized so that you could take the positive ones and have an inner product there, and the negative ones have an inner product there. They're going to equal the same normalized, um, basically, Dirac delta function, which is the point. Or we're just saying that when we go back to this point, the probability on both sides are basically uh, flips of each other, right? It's a complex conjugate. So we need that for for quantum mechanics to even work. Otherwise, it doesn't even work. Okay, and so we have this, and so essentially how we do a quantum state selection by doing a wave function collapse, and we have the Dirac delta function that chooses the wave function or it chooses the quantum state, and this kind of forces wave functions in this um, it forces wave functions in this 12-dimensional space to be forced into Hilbert spaces and normalizes them. And of course, we want this to be analytic, so it's got to be continuous, holomorphic, and there shouldn't be any unexpected singularities. So, um, it's just kind of a nice bonus on the side. Uh, and so essentially, we kind of lead to this idea that, well, we're kind of combining these two Laplacians. And when we do that, we could either do the positive version or the negative version. If we do the positive version, we get into the Kaluza-Klein modes. Uh, but if we go into the negative version here, what we could do some symmetry breaking. So we could find the differences between those two strings that flipped around the circle. Yeah. Again, what does that look like? These two, we could find the mass differences. Now, if this was perfectly symmetrical, then there would be no mass difference, and you would have 0 being equal to uh, the Hamiltonian here. So that gives us sort of this H0 no mass type of thing. But any slight imbalance would lead to a mass. So essentially we could take this closed string and flip it to an open string by taking 0 to pi. From 0 to 2 pi, we go to 0 to pi, and if there's any slight imbalance here, then that gives the graviton mass. And so that's the symmetry breaking, so that gives us essentially a Higgs boson out of this type of uh, oscillation. So there's another boson here. And so now we kind of basically have the standard model coming out of this strange 6 by 6 12-dimensional thing. Of course, there's um, the regular 4 dimensions too, but those are sort of back to 0. Um, I don't know, this is kind of an interesting way to look at things. Just having a little bit of fun. All right, so again, we kind of just recovered the standard model out of this. We have 12 oscillations in 12 dimensions. Just brings us down to 8 gluons, weak boson, and 1 photon. And then we have the Higgs over here, symmetry breaking. And and that's cool. See how we take a closed string, which would usually have 2 pi um, 2 pi around, but of course we're looking at the half pi state. And if there's any type of imbalance, then all of a sudden these zero mass photons, or these zero mass oscillations here, because these give you the zero mass, where the equal balance, and this one over here, as soon as you start to break it, it becomes the open strings. Closed strings to open strings. A little break right here. Interesting. So thank you all so much for watching, and hopefully